Okay, thank you, Alban. So today we have Xiaoyuan Zhang from the MPE in action. He got his PhD in Leiden, working on the physics of intercluster medium, and he then moved to Aachen to work with the eROSITA. And today he will be explaining us his results regarding the narration of the gaseous cosmic wave using eROSITA data. So please.
Thank you for introduction and invitation. Today I'm very happy to introduce the work from myself and our groups recent years about probing the dark regions, low density regions of the cosmic web, the gas there. And wait, I think I need to shift to here. Okay, yep, we can get rid of the problem. Wait. Is there a way to move this? Yeah. Okay, great. I think many of you are familiar with this cosmic web structure in the universe. These are from the recent category projects. A view of the gas density first, and it's basically follows the dynamic density on large scales, and just on some small scales it has some little difference. In the middle is the gas temperature, and you see the cosmic web is filled with hot gas, and the gas temperature is about 10 to the 6 Kelvin in filament, to 10 to the 7 in small halos, and to 10 to the 8 to massive halo center. And on the right is the sad thing that from X-ray, we can only see very dense regions, basically the center of the gaseous cluster. So in the vast space of the cosmic web, we don't really see them clearly. That's why we need to understand the physical properties of the gas in low density regions, how they are distributed, and what's the temperature, what's the density of them. And here is a more realistic view from real observations. We have our eROSITA or sky survey. Here is the image made by our colleague Jeremy Saunders. It shows you the Shapley supercluster. And we know the Shapley supercluster is a very massive supercluster around, not nearby. And from this image, we only see, okay, the sky background varies here. The color shows you different temperature on the sky background, the Milky Way gas. But for gaseous cluster, those very massive halos, we only see the X-ray emission from their center. And outside a few hundred KTC, the emission is below the background. So it's really difficult to directly probe those low density region gas by individuals. And either we need a very super deep exposure, or we can do multi-object stacking. And the reason, as I said, okay, here are the variance sensors done by more than 10 years ago, basically claiming like we have our knowledge for the intracluster medium, yes, for sure, but the intracluster medium we know is only 4% of the total barrier. And let's remove those low temperature gas, let's just focusing on the hot gas in cosmic web, then it's only 10% of the total kind of warm to hot gas population. So we only know the 10% of the hot variant that well in the low redshift universe. And we really like to know if we can understand the gas distribution in the cosmic web and how it suggests about the feedback from the agent or stellar feedback process. And on the right, I said we like to know the density, pressure, temperature, these thermodynamic properties of these gas, and also we like to know it's a single phase or multi-phase, or it's how complex they are. So in this talk, I will cover basically two projects. One is stacking of gaseous cluster outskirts, going away from the halo center, and the second one is cosmic filament stacking. They share some information, but they are different objects. And throughout this talk, I will use for plots from observations, I will mark them using purple border. If it's from numerical simulation analysis, I will use orange. And if it's observation compared with simulation, then I will use this transition border. So let's first have a look at the view in the outskirts. So let me first introduce like how big is the cluster halo. And here we take a very simple calculation, use NFW and use a high mass like 514 solar mass and put a typical concentration and put it at 0 redshift. Then for R500C, it is 1.2 megapascal. It's big. And then if we look at R200C, then it's almost 2 megapascal. Then the virial radius is 2.5, and the R200N basically is 3.2 MPC. That's very big. And on the right, I also put several different X-ray telescopes or observatories that how far they can probe the gas properties. So first, the Chandra. Unfortunately, Chandra, the particle background is high, and so basically we can only study gas within 500C. Then with the X-Newton, Suzaku, and the recently launched the Einstein probe, for X-Newton, because the collective area is big, so we can go to 500C, and for Suzaku, the background is low, so we can also go there. And for Einstein probe, yes, same reason. And for eROSITA, for individual source from the survey, it's impossible to go to that far. But this time we are going to stack many sources, and we will go to R200N. So for sure, in the past, people also try to stack classic cluster using survey data. The first prize from the Eckert, they stacked the eROSITA data basically 30 years ago. And on the right is from the Russian consortium. They did similar stacking works of 38 objects. They can claim they probe the emission out to 3 of 500. And this time, we'll try to stack more objects. So we have 680 objects, a factor of 20 more than previous stacking. And we select these objects in the low redshift and high, not really high mass, but in the mass of gaseous cluster region, massive halos. And on the right, you see the sky or the space sky distribution of those objects, because we don't like to include the high background or foreground regions. So we exclude those, and we only select objects from clean sky. And here it is an animation showing you how the signal to noise ratio improved by adding more objects. The first frame is very noisy, is only with 10 objects, and with adding more and more objects, the reconstructed image is very smooth. And on the right, it is the stacked surface primes profile. You see the framing of the error bar, and the inset is a zooming view of the around the background region. So we see after 100 stacking, we clearly see there's a trend, very smooth trend from the halo dominant to the background dominant region. So with this stacked profile in the last frame, we do our analysis. So first of all, we like to model our stacked surface primes profile. And for this time, we do see positive signal out to about 2 times R200M. So we have to deal with it carefully. So in this time, we try to use 3-component model to fit that. So the first one is typical one halo component here, means that the cluster, the gas halo associated with the clusters. And the 2 halo, we added that. It contributed by nearby things, could be cosmic filaments, could be nearby halos. And the third thing is uncorrelated background, because we stack multiple objects from the sky. Those uncorrelated components, they are really flat. So we do the decomposition, and on the right is the background removed profile. So let's focus on this background removed profile first. So the dotted line tells us where is the position of the sky background. It's super high, and the two halo signal basically is about 1% of the sky background, and we are probing the emission out down to this surface brightness level. And you might ask, what if we remove the two halo term and just fit one halo term plus a flat background? Does it work or not? So we do a model comparison. If we only fit with the one halo term, the residual getting worse, and the base factor difference is exp11. That's huge. So we have to add a two halo term to make the fit better. And it is very natural to have the two halo term out to this radius. So basically here the two halo term we use is the correlation function in the linear regime. And so now we have our fitting of the one halo term. It tells us what's the average the property of the halo we stacked. We can simply decompose it to get the density of the gas there. And because from the previous plot, we see that the one halo term, the signal, basically it ends at R200, and beyond that, it's very hard to probe that. So here we say the R200M is the outermost region. We can confidently say what is the gas density. And beyond R100M, it is the extrapolation of the model. So our conclusion here is at R200M, the baryon over density is about 30. It's not 1, it's 30. It means it's still an overdense environment at that far field. Now we like to understand what's going on in those regions, so we take illustrious TNG simulation to help us to understand the stack signal. And from the illustrious TNG, it doesn't matter if it really is illustrious or other simulation, it gives us similar conclusion about the outer part pictures. So let's just focus on this simulation data set we used. And on the left is the projected dark matter density, and on the right is the actual emission projected for tracing the gas. So you see really different pictures. So on the left, the sharp edge here, it traces the splashback of the dark matter halo. And on the right, you see the outside splashback, there's a shell of gas. So locally, these regions are gas rich and the dark matter pool. So also from the right plot, we see some structures like the accretion shock. It is the boundary between the hot gas shock heat gas and the void. And in the void, the gas is typical IgM with temperature about 10 to the 5th. A very cool gas, and after shock acceleration and shock heating, the gas temperature goes up to more than 10 to the 6th. Then we like to know what contributed to the two halo term we observed. So here we also do the similar stacking process using the TNG halos. We choose 159 cluster mass halos and do the stacking. And here's the stacked profile. And here we use different threshold to excluding the nearby halos. You see then the two halo term, the normalization is different. For sure, if we exclude more halos in the nearby region, then we get a lower two halo term normalization. But then we see that the project that with the 20 megaparsec project that the two halo term normalization is 10 to the 35 or less than 10 to the 35. And if you remember the plot I showed you before, we got similar order of magnitude if we convert the surface brightness back to the Earth per second per square. And if we try to understand, okay, what contributes to the two halo term, we like to know the details in different directions. So now we split the surface brightness, split the thermodynamic profiles into two types of directions. One is into the nearby cosmic filament. One is off cosmic filament, just hitting the voids. We clearly see the different trends into cosmic and non-cosmic filaments. So to the left, the temperature, you see that at about 2 times R400 M, in the filament region, you still keep about very high temperature, but if you go to the voids, temperature drops sharply. And the entropy is same. In the filaments, you have high entropy gas, but in the voids, it's really the flow of the entropy. And the pressure similarly, but the difference happens at the inner radius. So at about 1 times R200 M, we see the difference of the pressure in the two different directions. And similar for density at about R200 M, there's a difference. So from the inner region to the outer regions, within R200 M, different directions share the identical properties. Starting from R200 M, the pressure and the density in the filaments are higher, but and from the choice of R200 M, because it hits the shock boundary, so only in the cosmic filaments you still have the high density, high temperature, high entropy, and high pressure gas. And outside that, there's no hot gas anymore. So now we can see it means what? At R200 M, there's emergence of cosmic filaments or the halos from the cosmic filaments. That really tells us the signal we see outside R200 M must be from the cosmic filaments because they have high temperature and high density gas. And the X-ray emissivity is scaled with the density square, so it must be from the filaments. And at the boundary of the hot gas in the up filament direction is the accretion shock, because outside the accretion shock, you don't have any of this. And let's have a look of the two radii from our observed profiles. Now you see at the R200 M, our signal is starting to be dominated by the two halo term. It's a signature of the cosmic filament gas emits the X-ray we detected. And on the right panel, you see at the about 3 times R200 M, our best fit model cuts the average gas density of the baryon density at that redshift, our median redshift. It tells us approximately at that radius, the gas density meet the shock compression criteria, because the shock compression can only boost your density by a factor of 4. So basically, within the shock and outside the shock, the density difference is not that big. So that's why we choose this criteria to have a look where the shock is. And it matched the TNG simulation quite well. And if we focus on this comparison with TNG, then we see the clear difference of the slope or the density trend. And in the inner region, the TNG simulation tells us the halo average, the gas density is high and it drops quickly. But our result tells us at the center of inner region of halos, it's not as high as TNG shows. And in the outskirts, it drops slower. So the gradient is smaller than the TNG. So it tells us probably there is a stronger feedback in the real universe and on this cluster mass scale halos. And let me quickly summarize what we found by stacking halo outskirts. So this is a sketch from a few years ago Z-stacking, but I use that to tell you what we found. So first, okay, at R2M, we have a baryon over density of 30. Then at R-shock, our estimation is about 3 times R2M. And the two halo emission we see from the X-ray comes from the cosmic filament. And the connection between the cosmic filament to the halo atmosphere could be happening at a not very inner radius, but the R2M. So it's way inner than the shock radius. So cosmic filaments, these are structures penetrating the outer boundary of the hot gas. Okay, so now let's move on to the cosmic filaments. And here is the stacking work we did 2 years ago. We selected almost 1,000 cosmic filaments from the Malavasi 20 catalog. It's a SDSS boss-based tracer plus disperse algorithm. And we use a very soft energy band from eROSITA because in the hard energy band, everything is you stack is the agent from the cosmic filament. And only in the soft band, you can see something from the gas. And there are about 2,300 square degree common footprint. And you clearly see on this sky map, we don't have high surface brightness background regions. We masked them out. So we really chose a very clean sky footprint. And with those cosmic filament sample plus the source removed sky footprint, we removed all known sources from X-ray, and the richness higher than 20 halos. Basically, only unresolved gaseous groups are there, and unresolved things associated with galaxies are there. Then the error bar disappeared here. Anyway, there's supposed to be an error bar there, but it disappeared here. Anyway, so on the right we see weak but significant signal. Weak, it means that it's lower than 1% of the sky background. It's super weak, but the significance is non-sigma. But I would like to say it is the total X-ray emission. It's not a gas-only emission. We'll do it later to disentangle what's here the things disappeared. Okay, let me describe it. So we have two-step process to disentangle what is the diffuse gas emission and what is the halo associated dense gas but unresolved. So first we remove all known X-ray sources plus richness higher than 20 halos. And the second step, we estimate the residual contaminations. So it's also something to steal. Here, originally in this plot, there is our model plots, our model lines of the scaling relation. We use the scaling relation to paint galaxies from the legacy survey. Basically, we know the RA-back, we know the redshift, and we know the stellar mass of them. We can paint them on the sky and do the same stacking process to get the contamination profile. And on the right, there's supposed to be a contamination profile, and the normalization is about 40% of the total stack. So now we know that we have 40% stacked contamination, and we like to know further, after removing those components, what is the best fit temperature of the gas there? And on the right there, okay, there's also supposed to have some individual components of the undetected contamination, but it disappeared anyway. So we fit our stacked spectra. It's the signal to noise of individual beings is not really high, but still we get a temperature of 0.6 keV. So you might notice 0.6 keV is a hot temperature. It's not like what simulation tells us, like cosmic filaments, you have 1 million Kelvin, 1 million Kelvin gas. It's way hotter than 1 million Kelvin. That's why, because I believe that we have really selection effects of the temperature, because we have our observation window, we have our telescope effect area curve, and we also have the foreground absorption curve. So by folding those, we can only probe the hot gas higher than a certain temperature. For 10 to the 6 Kelvin gas, they don't emit anything in our band. Now we like to know the density of the gas that emits the X-ray we see. But it's very tricky because there are some degeneracies between the density and the length you use for interprobe. So here we take some literature profiles from Nimura 20. They stack the Planck TSZ, and because TSZ, they share different information. So we can combine X-ray plus TSZ to disentangle and some parameters. So on the left is our work, on the right is Terminal 20 TSZ stacking. They use the same filament catalog, so from the filament level, it shares similar properties. And we take additional assumptions. We assume there are two populations of gas. One is the majority volume filling gas, which is 10 to the 6 Kelvin, and that's rested by the simulations. And one is hot, dense, but non-volume filling gas, and we fix the temperature to what we get. They emit X-ray that we see. By taking that assumption, we get a estimated barium overdensity of 75 of that X-ray emitting population. And the volume fraction, filling fraction is less than 10%. So a few percent of the hot and dense gas in the cosmic filaments emits the thing we see. And on the right is the comparison between what we get and what's supposed to, not really supposed, what illustrates TNG suggests the phase distribution of gas in cosmic filaments. So we use disperse to extract the filament structure there, and we select the gas cells around the skeleton of filaments, and we exclude all known halos. So you don't see any halo particles, gas particles in this diagram. But you see on the bottom left, there's a straight line, but these are cool gas around outside of your shock radius, because the real filament structure is not really perfect. You always have some cool gas selected in your region. Anyway, let's focusing on the majority of this population. And if we apply SZ effect to see the gas pressure, then we trace the green circle. It's 50% of the total SZ effect from that region. And if we use 0.5 to 2 keV passband of X-rays, we can only trace the top right corner of this population, the hottest and the densest. And if we put our measurements there, it overlaps a little bit because our temperature is very high, and the emission weighted temperature is almost 10 to the 7 Kelvin. So it do tell us, okay, there must be multi-phase nature of the filament gas, and our stacked signal must be from some dense and high temperature population there. But now we have more questions. So after this project, so the first question is always like, the filament catalog we use, is that reliable? And because it's constructed using galaxies, and the galaxies are biased traces. And for the SDSS boss sample, basically these are red galaxies, luminous red galaxies. So probably the filament catalog we use, it only traces the most prominent filament structures in the universe. Then the second thing is like what we get about 75 baryon over density by stacking the filament, but it's higher than what we get previously from halo outskirts stacking, a factor of 2 higher, although they are at the same order of magnitude. But something tells us the extra emission now we see from filament stacking, it's some outskirts of some low mass halos, because we estimated the low mass halo emission, but it's difficult to really extrapolate your skin relation to the outskirts emission. You never know. It's probably what we see is the halo outskirts, and there's no clear boundary. Say where's the boundary of a halo outskirts? If you are a small gaseous groups, probably your outskirts is part of the filament. And then for the modeling, here we take some toy model. We assume cylinder geometry, but for sure, cylinder geometry is not that correct for this cosmic filament sample, because the cosmic filament sample traces most of prominent structures. Probably inside this structure, there's some substructure of the filaments, and a cylinder geometry probably is not that realistic. And also, in the future, we like to have some better profile modeling method, and to assume some other geometries, or forget about geometries and taking some other way to better fit that. And I hope in the future, with better method and a better filament cutter, we can have a more accurate constraint of the gas properties there. So, and here is my summary. So my summary, first, I like to say stacking of multi-objects using the large footprint survey is very powerful. And using eROSITA for basically those 2 years data, we get the signal into the accretion region beyond the atomic M of the halo. And using 8,000 filaments, we reach the non-segment total X-ray signal, and probably half of them are from the diffuse gas in cosmic filament. And for the 2 individual projects, I like to emphasize that, okay, we now really see the signal beyond atomic M, and we know the density well, average density well of gaseous cluster outskirts out to atomic M. And the comparison with the electricity G tells us that in the real universe, the feedback probability is higher than the TNG model, and it smooths out things on your smaller scales. And from the filament stacking, yeah, we know part of the gas physics there, but it's just the X-ray emitting phase. It's not the full filament gas. But still, we know some knowledge, and I like to address that the multi-phase modeling is challenging, but it's very important for us to understand the gas property there. So I will take questions now. Thank you.
Okay, time for questions. Thank you for the talk. I have a question, like when you talking about the cluster stacking from observation, and you compare the results with the simulations, and did want to compare the filament direction and off-filament direction. So when you do the observational cluster stacking, did you consider the direction of the filament?
No.
Just to do an average one.
No, because if we like to know the 2 directions, we like to know where is the filament in real observations. I'm not doing that. So the stacking, we use the 2 halo term basically to account the average the properties. So the true comparison, so basically that is the stacking of simulation without knowing the direction of filaments, and we see similar trends. I'll turn that. So it's flat.
question from an outsider in this field, right? So it's more connected to the techniques of the disperse that we have used to identify filaments. So how reliable are these filaments that we have identified in this data? I'm asking that because when applying disperse to data sets or to simulations in our medium performing regions, if the emission is very faint and very weak, you can create, so disperse will always try to find filaments and segments and tell you there is something there, but if the emission is weak, this is not necessarily a real filament. How?
No, that's very true, because currently the filament catalog I used, the tracer density is not really high. So it's SDS bars. And so I would say there must be a high contamination fraction in that filament catalog. The purity could be an issue, but if purity is an issue, it's okay, because it just randomly add you some random structures there and doesn't contribute to your signal. And then another thing I would like to say is because the tracer density is not really high, so by nature it smooths out the structures, right? So basically that's why we see in the stacked profile, it goes to 10 megapascal from the spawn. It's not physical, because filament from simulations always say like you have a radius of 3 megapascal, 2 megapascal. That here we see that just because of the tracer density is not that high. Smooth out.
So I have a question on the profile of the stack filaments clusters. Exactly what you expect with velocities and sort of the body of it. So yeah, the one inside. I was wondering, have I checked against other hydrosails with the programming thing that I was doing?
Oh yeah. So I didn't check, but there are a series of works presenting the feedback strengths for different simulations, and F-trace is one among the lowest feedback strengths, and magneticum is closer to our results, honestly. And Flamingo, because they can tune the parameters, so basically they can tell you, okay, minus several sigma is, or plus several sigma is closer to our results. And yeah, so we didn't check, but we can put this figure together with other plots from literature and to give you a feeling. But then I would like to say the sample selection could be different with mass selection. And people now more focusing on halos lower than 10 to the 14 solar mass and gaseous groups, basically. And there's a huge difference in gaseous groups. But now I would like to say in gaseous clusters, we also have this discrepancy.
Questions? Or any question online? I have one myself, also from our outsider. It's regarding your questions I think you have put in one of your slides. So what would you need to answer these questions? So more deeper observations, more
here, right?
Yeah.
So for the structure, the filament catalog, DESI will help us a lot. The tracer density from DESI is much higher than SGS. So if we apply the same method to DESI, then for sure we'll get better catalog of filaments. And another way to address that is we really need to do some simulation studies. Basically, from simulation, you know the halos and you know the true structures, and put a different threshold to select only those 10 to the 11 solar mass halos, and do the similar things to see the completeness and the purity of this method. These are two different things to address that. And for the second thing, I would say, it's also kind of, we can use cosmological hydrosimulation to tell us what's the best way. Because when you have like a project emission, whatever the extra emission or project a Z to a Z signal. It's a line of sight projection. If you take some line of sight extraction of gas particles, probably you know what is the depth, effective depth of them. And then it's better than use a cylinder model to model your cosmic filament. Because the cylinder model from our current catalog is very wide, and I put a smoothing factor there, saying like, okay, because of the tracer is not good enough, it's wide. But if we take some cosmic simulations and have some prior from there, it's much better, in my opinion.
Thank you. Last chance to any question. You're online. I don't know if there is any question online. Doesn't look like. If not, well, we can thank our speaker again. And we have to put this at a downtime maybe in a while. Thank you. Thank you.